So we continue with Nick's talk, and he will talk about the pieces of the Planetary Nebula puzzle with Gaia. Yeah.
Okay, can you see my screen?
Yes, perfect.
Perfect. Hi, my name is Nick Chornay. I'm a PhD student at the Institute of Astronomy in Cambridge. And I'm going to be talking today about using data from Gaia to study planetary nebulae. This is work with my PhD supervisor, Nick Walton, and a number of other collaborators who I'll thank at the end. My slide to advance. Okay, so the sort of textbook scenario for planetary nebulae is that they're the stage of life for stars between 1 and 8 solar masses. After the star leaves the AGB phase, it grows hotter and brighter before ultimately cooling and fading into a white dwarf. And the ultraviolet light from this hot star ionizes the expanding shell of gas that was ejected during the preceding phase, and that appears as a planetary nebula. So why are we interested in studying these objects besides the very pretty pictures? They're valuable probes of chemistry and dynamics in the Milky Way and many nearby galaxies. They offer insights into stellar evolution and different stellar populations. They provide a window into common envelope evolution, as many of them host close binary systems. And the OIII Planetary Nebula Luminosity Function is an important rung in the cosmic distance ladder. So what are the challenges then in studying these objects? They're only a brief moment in the life of a star, and as such, they're relatively rare, with only about 3,000 known in the Milky Way. There are open questions about the evolutionary pathways that lead to PN formation, particularly the role of binarity in common envelope evolution. And studying these questions has been hampered by the fact that distances to PN in our own galaxy have historically been highly uncertain and reliant on either modeling or statistical methods. Traditional methods such as isochrone fitting don't work because the planetary nebula central star is evolving very rapidly. So we're in this situation where it's actually been easier to study planetary nebulae in other nearby galaxies, because if, for example, you look at the PN in M31, you can just assume that they're all the same distance away from us. Unfortunately, you can't make that assumption for the Milky Way. So this is where Gaia comes in. As probably many of you know, Gaia is a space-based astrometry mission. It's providing positions, parallaxes, and proper motions for nearly 2 billion stars in the Milky Way. It also provides photometry in 3 different passbands. Eventually, it will provide low-resolution spectra and time series. The latest data, each successive data release will have better completeness and also improved precision in all of these parameters as they ingest more and more data from the mission. So Gaia is optimized for point sources, for stars, rather than for extended objects like planetary nebulae. However, it can do central stars of planetary nebulae, as well as distant and compact objects. And for these, it provides the parallaxes, which are a distance indicator, proper motions, which add another dimension to dynamics and complement the radial velocities that are relatively easy to obtain from the bright lines in the nebula. It also provides uniform photometry of central stars and variability indicators. And taking advantage of all of this requires being able to accurately match sources in Gaia with the central stars of planetary nebulae. So the remainder of the talk, it's going to be two parts. First, I'm going to talk about the cross-matching of PN central stars in Gaia, and then the second part of the talk about some different applications using this data set. So finding PN central stars in Gaia is essentially a cross-matching problem, but challenging for a number of reasons. They're very rare, but moreover, we don't actually have catalogued positions for most central stars. We have positions of the planetary nebulae, which may be offset from that of the central star for a number of reasons. And these positions also don't have uncertainties. And of course, we don't know if the central star is actually visible, or if it is visible, whether it will actually be the nearest source to the position of the PN. And there have been a few previous approaches to this. One is to simply use your planetary nebula catalog and take the nearest neighbor. While it is true that most central stars are actually the nearest neighbor for the PN position, this also introduces a lot of contamination into your sample. Another approach is to use manual inspection. This is time consuming and still quite error prone. Depends on what data is available, and it's difficult to quantify the uncertainties. The solution we adopted for this in our first paper is to use the likelihood ratio method. And this is something that's been traditionally used in the context of catalog matching, usually of sources from catalogs at different wavelengths. So the idea of the approach is to, the question it answers is, how do you separate a genuine PN central star from some field star that happens to be nearby? The idea is to compare basically the positional and color distributions of where you expect of true central stars versus those of background sources. And this works to some extent because color is actually very discriminative. Most central stars of planetary nebulae are quite hot, so finding a blue star near the center of the PN can give you reasonably high confidence that it is indeed a match. But by using both this and also the separation, you can come up with a metric that uses all the information that's available and doesn't necessarily discard stars that are not very blue because they may be binaries or heavily extincted. And the advantage of this approach is that it's consistent and fast and automated and works and easy to update with future Gaia data releases. And what we find is we're able to find central stars for about half of the objects in our sample. It's much more difficult towards in the galactic plane, in the bulge, where extinction is a lot higher, and also the density of stars is much higher. So just as an example of how this works, I've used here some images from the VFAST survey. One on the left is a planetary nebula, has a very blue central star. So these are UGR images. So the U band is quite discriminative for hot stars. It's easy to identify, it shows up as blue in Gaia. In case 2, there's a red central star, which is a known binary system. Our method selected it nonetheless because it's very central. Case 3, Gaia hasn't detected a central star, and it's not visible in the ground-based imagery either. But there is another nearby star, which other works had previously incorrectly identified as the central star, but we're able to reject it both because of its positional offset and its very red color. And then the last 2 cases show where there's some more ambiguity. The blue star is quite clear in the VFAST images. In one case, Gaia hasn't actually detected its color, and then it's we're not able to identify it, so it's not the closest to the center of the nebula. And in the final case, Gaia has detected the color, and our method correctly identifies the blue central star, even though it is not actually closest to the nominal position. So the real reason we care about this is because we want the parallaxes and the other data for these objects. Before Gaia, there were maybe only 20-odd parallaxes available for PN central stars. Gaia has been a huge increase in this number, and it's gotten even bigger with the most recent data release. Here, the numbers I'm showing are for parallaxes with a signal to noise greater than 1. So about a third of these are actually good enough, so a couple hundred, to really be useful kind of in their own right, but there's others are still useful in the context of priors or if you're studying kind of larger populations. And it's a huge improvement over also previous sets of primary distance measurements based on, for example, modeling. So we've got this large set of PN central stars. And in the second half of my talk, I want to talk about some of the applications for this data set and the things that we've been looking into. So if we go back to the sort of cartoon version of the post-AGB evolutionary tracks on the left, on the right, I've plotted the most recent central star tracks from Miller-Bartolomé. And what's key to note about these tracks in the sort of temperature luminosity space is that the higher the mass of the central star, the more rapidly the track evolves, and also the higher peak temperature and higher luminosity. So there's an issue in sort of planetary nebulae of these two different time scales. One of the how quickly does the central star evolve, and two, how quickly does the nebula evolve. So if you have a very low mass star, it might not actually get hot enough in time for the before the gas around it disperses. Whereas a very high mass star, you perhaps won't see the planetary nebula until it's already on the cooling track. So we can take these theoretical tracks and plot them on an observational Hertzsprung Russell diagram. So by assuming that, in this case, I've just gone and assumed black body spectral energy distribution. And what you see if you project these tracks into a magnitude diagram is that this sort of evolution, the first stage of evolution of constant luminosity to higher temperature actually appears as a dimming in terms of the visible absolute magnitude as more and more of the flux goes into the ultraviolet. So in the Gaia version of these tracks, the evolution is more or less consistently downwards in terms of the Gaia absolute magnitude. And the point where that corresponds to the peak temperature in the theoretical evolutionary tracks here corresponds about to a Gaia absolute magnitude of around 4. We've also plotted in this plot a sample of background sources, which will be mostly main sequence stars, and a white dwarf sample for reference. So now I can plot the set of objects that we've selected from Gaia. And for the first time, we can place a large number of them in the HR diagram. These are the ones that have relative parallax uncertainties better than 20%. I've also used the distances inferred from the Gaia parallaxes to plot the physical sizes of the nebulae with larger circles representing nebulae that are larger and probably therefore older and more evolved. So the first thing to note is that I think it kind of validates much of the selection in that The stars that we've selected clearly lie separate from the main sequence, and they're quite well explained by the theoretical tracks plus the effects of extinction, which kind of smear them downwards and to the right. The other interesting thing is that the more evolved planetary nebulae, so the ones that are the larger circles, appear sort of further along the tracks, so at a lower Gaia absolute magnitude. We can approximately, we can compare to these to literature extinction reddening values and use those to approximately de-redden. This moves sort of most of the central stars nicely onto the tracks, with some overshoot just due to uncertainties in the extinction and being a very approximate correction. There are still a few objects that kind of stretch out towards the main sequence. These could be simply that we've misidentified them and they're field stars, or also binary systems where light from the companion dominates. And indeed, if we compare to a literature list of binaries, many of them are in fact binaries. And here I'm using quite a broad definition of binaries, including also some objects where we've just, all that's been observed is infrared excess. Now, the question is there anything else that we can learn from the positions of these central stars in the HR diagram? Well, the color isn't by itself discriminative because, well, the color change with temperature is very small, and it's the extinction changes the color as well, so you can't really tell the difference. But what we can see is that I think the absolute magnitude actually does tell us about the position in the temperature luminosity diagram of these stars, because while the color doesn't change, the star will appear to fade in Gaia as more of the flux goes into the ultraviolet. So if you combine this with some assumption about, say, the time scale of planetary nebula visibility, in this case, maybe saying that taking a toy model where your planetary nebula is visible between 1 and 20,000 years after your departure from the AGB, what you find is that different regions of the tracks should have different masses of central stars showing planetary nebulae in those regions. So the lowest mass stars, when they become planetary nebulae, they'll still be on the constant luminosity region of the track, where they're evolving at increasing temperature, whereas the higher mass stars will evolve much more quickly, and when we see those as planetary nebulae, they'll already be past the peak temperature knee in the tracks and already cooling and fading. And so you can take the split in the temperature luminosity diagram and see this a similar sort of split just using the Gaia HR diagram. Now, is there any way to test this hypothesis? One is to look at nebular chemistry. We expect that the planetary nebula will reflect the abundances of the star that produced it, with higher mass stars resulting in nebulae with more nitrogen and helium. And so if we expect to say that the brighter central stars earlier in their evolution are indeed lower mass, and the fainter ones are more evolved high mass objects, we'd expect them to have different sets of different abundances. This is to some extent borne out by literature abundances, but it's very difficult to at least draw a conclusion immediately, because the sample that we're looking at is of abundances in general is far from uniform. Another perspective on this is also to use this classification scheme of Peinbert. So not only looking at the abundances, but also at the the location of the objects, their kinematics, and this is thought as well to relate to the progenitor stellar population and mass. The highest mass objects coming from the thin disk, and low mass objects, or thick disk objects. Low mass objects coming from the thick disk, and the lowest mass from the galactic halo. And the idea of this classification, this Hertzsprung 2007 work, was to take all of the parameters known about the object and assign it one of these classes, which then you would think relates to its mass. And again, there's some relation between the classes that they derived in this work, which was long before Gaia and based on a different set of data, and the positions of the objects that we see in the HR diagram. So it's something, this is all quite preliminary, but something I think is sort of an interesting way of looking at PN central stars, and something that's worth digging much more deeply into. So I think I've got, how many minutes do I have left?
Like 2 or 3.
Okay, I'll go quickly. So another thing to look at is variability. Binarity is very important in planetary nebulae. Also, close binaries in the centers of planetary nebulae are very important for common envelope evolution, in studies of common envelope evolution. The sample isn't huge, only 100 objects are known at the moment. But with Gaia, we can identify objects as photometrically variable from their uncertainties. And we've been looking at using this to identify new binary central stars of planetary nebulae. And there's a recent paper, Chornay et al. 2021, that goes into much more detail on this. But the sort of long and short of it is we can identify new candidates. A few of them actually have light curves from Gaia itself, which shows evidence that they're irradiated binary systems. And we're for the many other objects, we're looking at doing ground-based follow-ups. And the great thing about Gaia is that since we can identify objects that are variable in a fairly uniform way, we hope to obtain sort of a much larger uniform sample of binary planetary nebula central stars, which then feeds into both better population parameters for post-common envelope systems, and also it's easier to find more nearby systems that will be able to then follow up and model as individual objects. The very last thing, which is just more of a teaser, is we're also looking at the Planetary Nebula Luminosity Function. I'm going to sort of skip through this and say that it's important and interesting, and while it's not really used so much for distance scales anymore, it's also very interesting in terms of the sort of constraints it places on stellar evolution models and galactic star formation history. And for the first time, really, with these Gaia distances, we have some hope of actually trying to study it for our own Milky Way. So we've been working on a survey of narrowband OIII survey of nearby PN in the Milky Way, aiming to obtain a sort of volume-limited sample. And the sorts of results we hope to look at, so these are some objects from a run last autumn on the INT, relating their fluxes and distances. And then on the right, showing the OIII magnitudes versus the Gaia absolute magnitudes of the central stars, and sort of using that as a proxy for the evolutionary state of the central star of the planetary nebula, and that plotted against the absolute magnitude in OIII. And there's not a conclusion here, this is all very preliminary, but this is kind of the direction we're hoping to go, is to be able to actually study these objects in detail and figure out and look more into what types of objects form different regions of the Planetary Nebula luminosity function. So hopefully there'll be some more results for this. So in conclusion, Gaia is unlocking a lot of new avenues for the study of planetary nebula, from sort of stellar evolution to even an extragalactic distance scale. And it offers a new, sort of very uniform view of the galactic population and makes the sorts of these populations level studies possible that weren't really before. All of this work relies on being able to accurately cross-match the PN central stars in Gaia, which is what we did in our first paper. And the great thing about Gaia is that in the future, as the data gets better, this automated approach will mean that we can quickly adapt and benefit from data in future Gaia data releases. I just also want to thank, that's the end of the talk. I just want to thank my collaborators, Henri Buffon, David Jones, Marina Rejkova, and Roger Weston as well. Thank you very much.
Yeah, thank you too, Nick. I think that is really great work and was also a very nice talk. There's a question from Boris. Do you have some comment on the binary fraction of PN and whether / how this may affect the evolution?
How do I put it? So I'm not sure which, I don't know, in terms of the, looking at the position in the HR diagram and then what happens when that's a binary system, I honestly have no idea. So it's just all of that kind of is under the assumption of a single star evolutionary scenario. In terms of actually following stuff up, identifying things with new binaries, with the Gaia variability, with the kind of detection limits we have, it's probably like the sort of photometrically detectable fraction is still on the order of 20%, which I think is kind of the same as previous works with Ogle and Kepler, because there's still kind of a amplitude limit to the detectability. I might improve a bit in the distant future when we have the full light curves, because it's not very sensitive to things. Just using this photometric uncertainty isn't very sensitive to, say, just a system that's just eclipsing but doesn't have irradiation effects. But I think it's still roughly the same, kind of about 20%. But more, so the bigger benefit will be in just terms of expanding the sample of known binary systems, I think, rather than really being able to say much more about the binary fraction.
Okay, I will take one more question and then we will move to the breakout rooms. So George Jacobi is asking, are you able to derive a mass distribution function of the central stars and therefore the progenitor stars?
In theory, I've looked a bit into this. I think in theory you should be able to do, if you assume that there's a lot of steps involved, if you assume that the sort of the theoretical tracks and the visibility time scales, and sort of you should be able to then forward model a mass distribution into an observed distribution of central star absolute magnitudes. But there's, I think, a lot of complications in terms of completeness and selection functions and other things. So it's something I've started looking a little bit into, and I think there could be something quite interesting there, because if you can come up with some result based on the Gaia data alone, but I don't have anything conclusive.
Okay, then thank you very much, Nick, again. We will move to the breakout rooms now.